All right. Um, all right. Ecde level 4. We're going to be exploring question 1. So if you notice, if you've been working with past papers, you will notice that question 1 is going to cover topic 1. Question 2 is going to cover topic 2. Question 3 is going to cover topic 3, and question 4 is going to cover topic 4, and question 5 is going to cover topic 5. I'm not sure if it's always going to be like that, but in most papers we've tried to explore that is the case. So we're going to explore question 1, which is topic 1 actually. So element of focus. So usually here you are dealing with RLC theories. So RLC theories, which means you go from current versus voltage in a purely current versus voltage in a purely resistive circuit. So you have to explain the behavior of current versus voltage in a purely resistive circuit, current versus voltage in a purely capacitive circuit, inductive circuits, current versus voltage in a purely capacitive circuit. So you should be able to explain the behavior of current versus voltage in this type of circuit: resistive circuit, inductive circuit, capacitive circuit. Should be able to explain what is reactance. You should be able to explain what is impedance. So we're going to go through all that quickly as we're going to solve a 2023 question paper, if I'm not mistaken. So you should be able to, so we're going to be dealing with RL calculation, RL circuit, series RL circuit calculation, and then you also focus on the relationship between current and voltage in a series RL circuit, series RL circuit phasor diagram, effect of faulty component. Please don't forget this, because I've seen these questions: effect of faulty components on all type of circuit, RL, RC. So here, for example, from point 10, we focusing on series RC circuits, relationship between current and voltage in a series RC circuit, series RC circuits phasor diagram. We do the phasor diagram because they would ask you to draw the phasor diagram. I've seen like 4 or 5 question papers where you are being asked to draw the phasor diagram, or they've given you the phasor diagram and they ask you questions based on that phasor diagram. Effect of faulty component, again in a RC series circuit, so we're gonna have to discuss on that, or you can read through that also. Okay, point 14, we go series RLC. So this is the combination of the 3 of them. So if you notice, up above we've done RL. So this is what we're doing. We've done series. So on one side we do series, and on the other side we do parallel. So first of all, they are coupled in 2. First of all, it's single one. It's R. Well, R to itself, you cannot say it's parallel, of course, but you have to know the behavior of current and voltage in the R circuits, in a L circuit, which is inductive circuit, in a C circuit, which is capacitive circuit. So that's it. But mostly the focus is on series and parallel circuits. So we do RL series circuits, RL parallel circuit, RC series circuit, RC series circuit. Now we combine the 3 of them: RLC, RLC. So that's the area of focus. Now, while you're studying that, you should not forget the relationship between current and voltage in all this type of circuit. You should not forget the effect of faulty component in all these circuits. So this is what we've listed from point 1 all the way to point 27. So we're going to try to explore through the formulas, through a few things. So what I can easily say, so this is what we can say. Let's go through. So in a purely resistive circuit, what do you know about resistive circuit? A resistive circuit, we are talking about, this is AC theory. Of course, we are discussing AC theory, which is exploring topic 1, AC theory. So in the AC theory, a resistive circuit is actually when a resistor alone, a purely resistive circuit, is connected across an AC power source. So that's what we are exploring. So the voltage across, there is a current flowing in the circuit. So what is the behavior of current versus voltage in a purely resistive circuit? Current and voltage are in phase. So we say they are in phase. You will notice even when they ask you to draw the phasor diagram. Phasor diagram is only a representation of current and voltage through the vectors. So you're going to have, so they are aligning in parallel like that, just to show that they are flowing in the same direction. So that will be the current vector, and that will be the voltage vector. So they are aligning like that. So which means they are in phase. Whatever happening. So if the voltage, so if you have to represent it with a sine wave. So if this is the voltage sine wave, the current sine wave, so they are all, doesn't matter what amplitude the current is. So when the voltage is rising, the current also rises. As it's falling, the current also falls, and so on. So this is what they mean in phase. It means they reach 90 degree at the same time, and they reach 270 degree at the same time. This starts from 0 at the same time. So in a resistor, this is what happens. This is where the Ohm's law is based, because actually you say that the current flowing into a resistor is directly proportional to the voltage, and inversely proportional to the resistor. So this is actually what's happening there. In an inductive circuit, here, what happened in an inductor? What happens when an inductor is connected across a AC source? What happens then? There is a voltage across, and there is a current flowing into the inductor. So what happens? We say that when an inductor is connected in a purely inductive circuit or across an AC source, the voltage leads the current by 90 degrees. So that's what happens. So if you have to draw the phasor diagram, as I said, it's a representation of voltage through vectors. So we're going to have the currents represented like this, horizontally, and our voltage. So leading means it's pointing up. That's what leading is. It's pointing up. That's it. That's what happens. So the voltage VL, which is the voltage of the inductor, is leading the current in the circuit by 90 degrees. So that's it, 90 degrees there. So that's what happens in inductive circuit. And we know that capacitive is the opposite. Capacitive is a complement of an inductor. So everything that happens to an inductor, the opposite happened to the capacitor. What happens in a capacitor? So if the voltage was leading in a capacitor, in an inductor, in a capacitor, the current is going to lead. So current leads. So when a capacitor is connected across an AC source, what happens? The current leads the voltage by 90 degrees. That's what happens. Current leads the voltage by 90 degrees. So the current flowing into the capacitor leads the voltage by 90 degrees. And if you have to do a phasor diagram representation, so you're going to have your current there. And what happens? The current is leading, which means your voltage is lagging, because you have two words there. Lead, it's taking the lead, it's in advance, and lag, which means there is a delay. It's late. So leading would be pointing up, as we said. So here on the inductor, leading, the vector was pointing up. So in the capacitor, the current is leading. What does that mean? It means the voltage is lagging. Lag means there is a delay. So 90-degree delay, so which means it's going to be pointing down. So that will be your VC. So your VC there is pointing down. Late by 90-degree. Delayed by 90 degrees. So that is, or out of phase, because you can say here the resistor is in phase with the current. So voltage and current are in phase. Voltage and current are in phase. Here voltage is out of phase, so which means with the voltage leading, of course. Here that is the inductor. With the inductor, the voltage is out of phase with the voltage leading. With the capacitor, the current is out of phase with the current leading. With the current leading. So that's it. So when the voltage is leading, the vector is pointing up, and when the current is leading, which means the voltage is lagging, so the voltage is going to be pointing down. So that's how it is. All right. Point 4. Explain reactance. Reactance is like resistance. What is resistance? Resistance, we know that resistance is the opposition of current flow in the circuit. So we know that resistance is opposition of current flow in the circuit. Same thing applies with inductance. So with inductance, we also know that inductance is the opposition of current flow in a inductive circuit or capacitive circuit. So that's actually the definition. Here the focus is more on the circuits, inductive circuits. So if they ask you reactance in general, it is the opposition of current flow in an inductive circuit or in a capacitive circuit. If they specify what is capacitive reactance, then they've specifically asked you about a given circuit. But if they ask in general, describe reactance, opposition of current flow in an inductive circuit or in a capacitive circuit. So when the reactance is happening in an inductive circuit, it is referred to as inductive reactance, XL. When reactance is happening in a capacitive circuit, it is referred to as capacitive reactance, XC. And we're going to see when we start calculations that even the formulas, so they kind of oppose each other. So XL, which is inductive reactance, is going to be 2 pi F L for inductance. So the value of the inductance they're going to give you is going to allow you to calculate, and the frequency which is going to be given also is going to allow you to calculate the inductive reactance. And if they ask you to calculate the capacitive reactance, you do 1 over 2 pi FC. C stands for capacitance. So the value of the capacitor they're going to give you and the frequency they're going to give you is going to allow you to calculate the capacitive reactance. So point 5, impedance. So impedance is the total resistance. Total resistance in an AC circuit. So impedance, and the notation, the symbol that we're going to use to refer to impedance is the letter Z. So that's the notation for impedance, Z. So when we do calculations, we're going to one more time also describe how to calculate the impedance. Point 6. So you're going to notice from point 6 we're already introducing the calculations. So what we have done, the simplest way we are doing this is on one side we're going to discuss series circuit. On the other side, we're discussing parallel circuits. So we're coupling them first as RL, RC. So R stands for resistance, we know that. L stands for inductance. So RL, which means resistance and inductance in series. RL, resistance and inductance in parallel. RC, series. Series RC means resistance and capacitor in series. RC parallel means resistance and capacitor in parallel. And the three of them now combined, RLC, series means resistance in series with an inductor, in series with a capacitor. And then RLC parallel means resistance in parallel with an inductor, in parallel with a capacitor. So we exploring them in that manner. So you're gonna notice that for every type of circuit we're gonna do, we are going to be discussing the relationship between current and voltage in that type of circuit. If it's a RL series, we're going to discuss the current and voltage, the behavior, the relationship between current and voltage in a series RL circuit, in a series RC circuit, in a parallel RL circuit, in parallel RC circuit. So this helps you easily draw the phasor diagram, because remember, we've done the phasor diagram for each component, for a resistor itself, for an inductor itself, for a capacitor itself. Don't forget the basis of what we have done, because from that basis we should be able to describe or to define the phasor diagram of each circuits with a combination of RL, RC, RLC, series or parallel, based on the relationship between current and voltage. This is very important. So I'm going to go to another page. So here we summarize formula sheet for RLC series, but mostly now we are exploring the behavior that's going to help us draw the phasor diagram. Let's study this behavior. And this helps you, instead of just memorizing each phasor diagram, you know exactly what to do. So your reference is first the introduction that we did when it came to resistive circuit. What did we say about resistive circuit? We said that resistive circuits, in a purely resistive circuit, the voltage and current are in phase. In phase, that's what we said. So in phase, what does that mean? It means when you draw the phasor diagram, the voltage phasor diagram is going to be there. In phase means they're pointing to the same direction as the current is pointing the same direction as the voltage. That's what the phasor diagram in phase means. So in an inductive circuit, because RL that we're solving here, this RL circuit, RL means resistor and inductor. In an inductive circuit, what happens? The voltage leads the current by 90 degrees. So that's it. Voltage leads currents by 90 degrees. So what does it mean in terms of phasor diagram? In terms of phasor diagram, it means the current is our point of reference, and it's going to be drawn horizontally like that. And then, sorry, let me create some space. So it's going to be drawn horizontally like that. That's our current. And then the voltage is going to be pointing upward like that, and that will be your current, your voltage. So that's what it means to lead. If it was lagging, if the voltage was lagging, it was gonna point downwards. When it's pointing upwards, it means it's leading by 90 degrees. So now in our case, where we have a resistor in series with an inductor, so you won't even need to read this whole theory, because the theory that we have here is when a resistor is coupled in series with an inductor in an AC circuit, the voltage across VL, the voltage across the inductor leads the current by an angle between 0 to 90 degrees. So we know that, but you won't even have to memorize this whole statement if you have your basic theory here. So this basic theory that we have done here for an inductive and a capacitive circuit, this basic theory is going to help you draw the phasor diagram. So first of all, you draw when the circuit is given like this. So we have a RL circuits. So what is the one thing we know about a series circuit? This is a series circuit. What is the one thing we know about a series circuit? We know that in a series circuit, the current remains the same. The current does not change. So the quantities that does not change becomes our point of reference. Every time you are dealing with the circuit, the quantities that does not change becomes your point of reference. We know that in a series circuit, current remains the same, but there is a different potential drop across each component. A resistor is going to have a voltage across it, and an inductor is going to have a voltage across it. So VR is going to be there, VL is going to be there, but the current is going to remain the same. So which tells us exactly what we're supposed to do, because if you check, when you are dealing with the resistor, how does the voltage VR is going to behave first versus the current? The voltage is going to be in phase. Yeah, we are defining here. And how are the voltage is gonna behave versus the current? The voltage is gonna lead the current. End of story. That's how you can draw your diagram. So you can come here when they give you any RL series circuit and they ask you to draw the phasor diagram. Your point of reference is the element that did not change, which is the current did not change in a series circuit. So your current is there. How is your voltage, resistor voltage? The resistor voltage is going to be in phase with the current. So that is your VR. How is your inductor voltage? Your inductor voltage is going to lead the current by 90 degrees. That is your inductor vector, VR. So, and then the last thing you have to do is you just project there, and then for you to be able to determine your total voltage. That's it. That's how easy this is. Let's do parallel. Parallel means your resistor is in parallel with your inductor. So that's it. That's what you do. Both connected across an AC source. What do you know? What is the one thing you know about a parallel circuit? It's that the voltage remains the same. Voltage is going to remain the same, but each component is going to have a different current flowing through it. An inductor is going to have IL flowing through it, and the resistor is going to have IR flowing through it. So that's how it's going to be. So you understand that when you are dealing with a parallel RL circuits, how is the current versus the voltage in the resistor? The current is in phase with the voltage. Easiest thing. There we are there. Now, in parallel, how is the current of the inductor versus the voltage? The current, so here it says the voltage leads the current. What does that mean? It means the current lags. The current lags the voltage. That's what it means by 90 degrees. It's actually the same statement, if you follow me. So the current is lagging, so we have to draw this phasor diagram. It's much easier because what is our point of reference? It's the voltage, because the voltage is the only thing that does not change in the circuit. The voltage is our point of reference. How is the current of the resistor versus the voltage? They are in phase, so I'm gonna have to draw it there. That's IR. How is the current of the inductor versus the voltage? It's lagging. It's going to point down there. That's IL. So we're going to have to project a little bit like that, and then like this to the IL, and then draw our total current. Easy. So easy like that. Just like that. Let's go to RC circuit. RC circuit. Let's do the same thing with RC circuit. Remember your point of. Remember the elements. The foundational element is how is current and resistor behaving in a resistive circuit. This is RC. RC means we have a resistor and we have a capacitor. So we're gonna define the behavior of current first. That's the first thing you tell yourself. You define the behavior of current and voltage in a resistive circuit. What happens? Voltage and current are in phase. In phase. What does that mean in terms of phasor diagram? This is the voltage vector, and then in parallel there is the current vector. So they are pointing to the same direction. That's what it means in phase. Capacitor. For a capacitor, how is voltage versus current in a capacitor? In a capacitive circuit, the current leads the voltage by 90 degrees. What does this this statement also means that the voltage lags the current by 90 degrees. The voltage lags the current by 90. That's what this statement also means. So the current lags the voltage lags the current by 90 degrees. So it's the same statement. You remember now. So now, how is the phasor diagram? So the phasor diagram is going to have the current as point of reference and the voltage pointing down like that. So there is our current and there is our VC pointing down like that. So that is our drawing, 90 degree there. So now let's go to the circuit. So if we have a series capacitor RC circuit, RC means resistor in series with and in that a capacitor, with the capacitor both supplied by a AC source. So we have something like this. Again, this is an RC circuit. Again, what do you know about a series circuit? In a series circuit, the current is going to remain the same, but the voltage across the resistor is going to be different, and the voltage across the capacitor is going to be different. So we're going to have one current versus two voltage drops. So that's what happens. So we know already. How does the voltage in the resistor behave versus the current? The voltage in the resistor is in phase with the current. How does the voltage behave in a capacitor versus the current? In a capacitor, we know that the voltage lags the current by 90 degrees. So that's what happened. The current is actually leading the voltage. The voltage lags by 90 degrees. That's what we know. So let's go to the phasor diagram. In series. So let's draw. What is the common elements? Our point of reference is going to be the current. Why do we start with the current? Simply because the current is the only thing in the circuit that does not change. That's what you should know. Now, how is the voltage of the resistor versus the current? The voltage of the resistor versus the current is going to be in phase. So that is our VR. Good. Now, how is the voltage of the capacitor versus the current in the circuit? The voltage of the capacitor versus the current, they say the voltage lags the current by 90 degrees. It's going to point down. Lags means it's going to point down. So that's what happens. So this is our VC. Now what do? We just project our point there, and then we obtain our V total there. That's it. So that's how easy it is. In parallel, let me create some space. In parallel, so you won't even have to memorize the theories that are written about the behavior of current, relationship between current and voltage in RC circuits, if you know how to do this. So RC parallel circuits, so we're gonna have supply there with an AC, and then we have this, we have that. So RC. What do we know about a parallel circuit? We know that in a parallel circuit the voltage remains the same. That's what we know. And each component has got a different current flowing into it. The capacitor is going to have IC flowing into it, and the resistor is going to have IR flowing into it. So it makes it easier. So if we go back to analyze our foundation that we laid there, we're going to notice that in a resistive circuit, how is the current in the resistor versus the voltage? In the resistor, the current is in phase with the voltage. That's what we get there. How is the current versus the voltage in a capacitor? The current versus the voltage in the capacitor, the current leads by 90 degrees. The current leads the voltage by 90 degrees, so we know that. Or the voltage lags by, we know that. So what is our point of reference in a parallel circuit? Our point of reference is going to be the voltage. So we know that already. So our point of reference is the voltage, and it's going to be a horizontal, voltage we said. It's going to be an horizontal vector. Now, how is the current of the resistor versus the voltage in a circuit? The current of the resistor versus the voltage is going to be in phase. So that's the current of the resistor. Now, how is the current of the capacitor versus the voltage? The current of the capacitor, they say the current leads the voltage by 90 degrees. So it's much easier. We just have to come here and draw. Its leading means it's pointing up there. That's what we have. So that is our IC. And then what do? We just project it like that for us to determine our I total. So you understand that series circuits, we are exploring more voltage. So in a series circuit we explore voltages. In a parallel circuit we are exploring. So that's why in a series circuit there is only one current, so which becomes our point of reference. In a parallel circuit there is only one voltage that becomes our point of reference. So in a series circuit we are exploring into the voltage because we have different voltages. In a parallel circuit we are dealing with current. It's a current circuit because we have many currents and one voltage. So you have to be able to split all that so you know which one is your point of reference and you know how to draw the phasor diagram. Okay, so for our RLC circuit combined, so how do we determine the phasor diagram? First, on the basis of what we have done. Remember, we discussed about a resistive circuit. In a purely resistive circuit, what happens? The voltage and current are in phase. So are in phase. So they are in phase. So what does that mean in terms of phasor diagram? So which means the voltage horizontally pointing to the right, V, is in phase, which means the current also parallel and horizontally pointing to the right, same direction. So that's what it means, they're in phase. For an inductor, we say that an inductor, the voltage leads the currents by 90 degrees. Leads currents by 90 degrees. So this statement can also be put as the current lags voltage by 90 degrees. So that's what the statement can go. In terms of phasor diagram, so we're talking about current being horizontally pointing to the right like that, and then the voltage pointing upward. So that will be that. And for a capacitive circuit, because this is defined as inductive, so we define this as inductive. And for a capacitive circuit, the current leads voltage by 90 degrees, or voltage lags currents by 90 degrees. So what does this mean? This is capacitive. What does this mean? It means that you have the current pointing horizontally like this to the right, and then your voltage there pointing downward, so 90 degrees there. So that's what we're talking about. But there is a little bit of something to remember when it comes to RLC circuit. Remember, this is L and C. So how do you decide, or how do you know when it's an inductive circuit or when it's a capacitive circuit? So this is what we do. Let me draw the circuit, then we're going to define it as an inductive circuit, as a capacitive circuit, and as a resonant circuit, because that's what should happen. So resistor in series with an inductor in series with a capacitor, and both of them supplied with AC. Now this is what happens. R, L, C. So what do we know about any series circuit? We know that the currents remains the same. That's our point of reference. That is going to be our horizontal vector. So, and then in any series circuits, there is a voltage drop across each component connected to it. So we're going to have a VR, we're going to have a VL, and a VC. So each component is going to have its own voltage drop. But we talk of inductive circuits. That's number one. A circuit, an RLC circuit, is said inductive. First of all, when XL is equal to XC. When XL is bigger than XC. So when XL is greater than XC, we talk about inductive circuit. But in this context, we don't have XL. We are not referring to XL. So what are we referring to? Or when VL is greater than VC, we talk about inductive circuit. But yeah, this statement, most of the time in the exam, you don't have to bring it up. But usually in the context of our phasor diagram, since we are working with voltage, that's why I have to bring it in. So VL is greater than VC, it's an inductive circuit. What does that mean? This means that I should be taking a different color. This means that, let me take color, black, take blue. Okay. So this means that if the circuit is said to be inductive, the voltage drop that we're going to consider here for an inductive circuit is going to be VL minus VC. So that will be our vector there. So when we are drawing the vector, our vector is going to be VL minus VC. So again, we are referring still to this resistive circuit, inductive circuit, capacitive circuit. We are still on this, but without forgetting that now we are not just using the vector called VL, we are using the vector called VL minus VC. So because we have three components, the R, L, and C. So we are using a vector called VL minus. So it means if we have to draw the phasor diagram, so we know that for our phasor diagram, so let me just save some space. So in a series circuit, there is only one current. The current becomes our point of reference. So there is our current I. Now, for our resistor VR, how is VR versus the current? VR is in phase with the current, so VR is going to be there. That's our VR. Let me write VR on top there. That's our VR. Now, instead of checking the behavior of VL or VC versus the current, we're going to check the behavior of VL minus VC. Why? Because we are dealing with an inductive circuit. So in an inductive circuit, our vector is called VL minus VC. So inductive circuit. So VL minus VC, what does it say here in an inductive circuit? It says that the voltage, in our case here, for an inductive circuit, in this case, the voltage here is VL minus VC, leads the current by 90 degrees. What does that mean? It means we're going to draw it pointing upward like that, and then we write VL minus VC. That's the name of that vector there. VL minus VC. And then what do? We just project there, and we get our V total. So this is the case of inductive circuits. What what if we are dealing with what if the RLC, R here, L and C in the circuit are, we get a capacitive circuit. In a capacitive circuit, if we have RLC, let me go back to the color red. So if we are dealing if R, L and C give me a capacitive circuit, produce a capacitive circuit, what does that mean? It means that XC is greater than XL, or VC is greater than VL. So already you know that the vector is called VC minus VL. So we are dealing with a capacitive circuit. And how does the voltage behave versus the current in a capacitive circuit? So we go back to the circuits there. Let's check the circuit here. So we have here, so this voltage across inductor and capacitor, let me go back and put color blue back again. So this voltage here now is not VL minus VC, it's now VC minus VL, because in case where your voltage, your capacitor voltage is greater than your inductor voltage, so that circuit is said to be capacitive. So that would be our vector there. And what happened in a capacitive circuit? In a capacitive circuit, the current leads the voltage by 90 degrees, which means the voltage lags the current by 90 degrees. So the voltage is lagging. The voltage lags the current by 90 degrees. So what does that mean? We have one current. We have, I'm going to draw this, it's going to be faster. So we have one current, which means that's our point of reference, a vector pointing to the right and with I. So how is the voltage of the resistor versus the current? It's in phase, so that's going to be like that. Now, how is the voltage, the capacitive voltage, because it's a capacitive circuit? There is our capacitive voltage. Our capacitive voltage is VC minus VL. That's it. So how is, they say in a capacitive circuit, we are back there, they say in a capacitive circuit, voltage lags current by 90 degrees. So VC minus VL is going to be pointing downwards like that. And then we project. So this is our VR, this is our VC minus VL. So we project there for VR, and then we obtain our V total. There, that's it. So that's the phasor diagram for a capacitive circuit. So that's how you draw the phasor diagram. So from there, I believe it's easy for you to continue and draw the rest of the phasor diagram, because you're going to have the phasor diagram for a resonant circuit. Number 3, for a resonant circuit. Resonant circuit means RLC is RLC, resonant circuit. What does that mean? It means XL is equal to XC, or VL is equal to VC. So which means they are both equal. So it's going to be easier for you to draw the phasor diagram for that, and then to draw the phasor diagram for a parallel circuit. But this is the basic idea, the concept, so you get the idea of how to draw it. Alright, so useful formulas that we can use, because the challenge that we have is the formula sheet does not provide us with enough formulas. Does not provide us formula based on the problem that is in the examination, and so you have to know, somehow you have to know your formulas. You don't have to rely on a formula sheet. So we already determined that XL, which is the inductive reactance, is going to be calculated as 2 pi multiplied by frequency multiplied by L. L is the inductance. So the value of the inductance is given to you, and you must always determine your inductive reactance. XC is your capacitive reactance, so which is 1 over 2 pi FC. C is the capacitive reactance. So frequency and capacitive reactance will be given to you. But after that, so we are dealing with series circuit. Let's discuss series circuits formulas, then we're going to discuss parallel circuit formulas. So we've done the tutorials with where we were trying to establish the difference in terms of formula of series circuits and parallel circuits. So let's discuss series circuits. So series RL, it can be RL or RC or RLC circuit. So all the three combined. So when you are dealing with the series circuits, so we're gonna discuss about ILC later. So when you are dealing with a series circuit, the first thing you need to know, they will usually ask you to determine the impedance. Not all the time, but this is a general case where you ask to determine the impedance. So when determining the impedance in a series circuit, you apply Pythagoras formula. Apply the Pythagoras formula, the triangle, where you are calculating the apparent angle, so the Pythagoras angle. So if you are dealing with the RL, so your Z is equal to square root of R is your A squared plus XL is your B. So that's how you determine. So when you are dealing with the RC, your impedance is going to be equal to square root of R squared plus XC squared. But if you have a case where you are dealing, you see this angle here, this the next angle. When you have a case where you are dealing with RLC, the case of RLC here, the circuit is either inductive. When the circuit is inductive, when your circuit is inductive, it means XL is bigger than XC. So that angle is going to be XL minus XC. So that's it. When you are dealing with a capacitive circuit, so because the RLC circuit can be capacitive. So when it is capacitive, which means XC is bigger than XL. So what does that mean? This means XC minus XL. That's what you do. So it means when you are calculating for RLC, when you are calculating your angle, when you are dealing with inductive circuits, you're going to have square root of R squared plus XL minus XC, everything squared. That is for inductive circuit. If your circuit is capacitive, what do? Z is equal to square root of R squared plus XC minus XL, everything squared. So that's what you do. So the next thing you want to know, they would ask you to calculate the current. So the next thing is current. So for current, apply simple Ohm's law, because obviously you are dealing with a problem where they've given you the voltage, the applied voltage. So just apply Ohm's law. So your Ohm's law for current in a series circuit, there is only one current. So your formula is V, which is the total voltage, the applied voltage, over Z. Z, remember, impedance, we said impedance is the total resistance in an AC circuit. So every time you are determining the impedance, you are actually calculating the total. So since in series there is only one current, you don't need to write total current. You can just write total current, doesn't matter, but there is only one current. So you're going to have to do V total, which means the supplied voltage divided by the impedance. Impedance is also a total resistance. Don't forget that. So number three, you can be asked to calculate the phase angle. So the angle. For the phase angle, you have to be careful for the phase angle. So phase angle, calculating the phase angle, that's the phase angle. So when you are dealing with the RL circuit, for RL circuit, your phase angle is equal to 10 to the power negative 1 multiplied by XL over R. R is always the denominator. If you are dealing with RC, so your phase angle is 10 to the power negative 1 XC over R. If you are dealing with RLC, if the RLC is an inductive, because even also here, remember here, if it's an inductive circuit, you are dealing with XL minus XC as a numerator. If it's a capacitive circuit, if it's an inductive circuit, you are dealing with XL minus XC as a numerator. If it's a capacitive circuit, you are dealing with doing XC minus XL as a numerator. So that's exactly what we're going to do here. So the angle is going to be, for an inductive circuit, 10 to the power negative 1 XL minus XC. This is for an inductive circuit over R. R is always the numerator. If you are dealing with a capacitive circuit, so you go 10 to the power negative 1 XC minus XL over R. That's how you calculate your phase angle. They might also sometimes ask you to calculate the voltage drop across each component. For voltage drop across each component, which means VR or VL or VC, just apply simple Ohm's law. Ohm's law suffice here. Just apply a normal Ohm's law. So for VR, what is the formula for Ohm's law? It is I times R. For VL, what is the Ohm's law formula? It is I, because in a series circuit there is only one current, times XL. Please, Ohm's law, remember, not L. The resistance for inductance is XL. There. Pay attention there. So when you are dealing with capacitor VC, the resistance for capacitor, you do I, because there is only one current, there's going to be only one current, multiplied by XC. Your resistance for capacitor is XC. So these are the possible questions they can ask you when you are dealing with a parallel circuit. Remember, I'm going to insist here again. Check for me here. For a series circuit, every time they're going to ask you for a impedance formula, you apply the Pythagoras formula. When they ask you for current, you apply Ohm's law. It's going to be the opposite in a parallel circuit. So in a parallel circuit, I'm going to continue. In a parallel circuit, when you are dealing with parallel RL or RC or RLC combined circuit, so in a parallel circuit. So here again, we're going to talk about RLC in this circumstance again. So one, usually they will ask you to determine the total current. Usually they will ask you to determine the total current. For you to be able, so here we apply Pythagoras formula. So apply the Pythagoras angle here. So, but first of all, you need to be able to determine the value of each one of them. It can be IR, the resistance flowing through the current, or IL, resistor flowing through the inductor, or IC, resistor flowing through the capacitor. You should be able to define all of them. So which means if you are dealing with the RC circuit, they ask you to determine the total resistance, the total current, the total current is going to be square root. So after you've calculated IRR, so you have to determine, so RC, which means here you need to know the resistance for the IR and IC. That's what you have to know there. So here you apply your total current is going to be IR squared plus IL squared. That's what you do. If here we are dealing with the IL. IL. I was talking about IL, not I was talking about IL. RL. So in RL here, you determine your IR and your IL. After you've determined them, then you plug them in a total current formula. Remember, in a parallel circuit, when you are asked to calculate the total current, you apply the Pythagoras formula, but you must first determine your IR or your IL or your IC. So then but in the circumstance where they ask you to calculate R in an RC circuit, so in an RC circuit, first you must determine your IR, then you've determined your IC, and then you can calculate your total current by saying square root of IR squared plus IC squared. Good. But what if you are dealing with RLC combined? So if you are dealing with RLC combined, you should first of all know, are you dealing with the case where IL is bigger than I? So after you've calculated IR, IL, IC, what did you find out? Did you realize, is your IL bigger than IC? So if your IL is bigger than IC, what you have to do is IL minus IC. If your IC is bigger than your IL, what you have to do is IC minus IL. That's what you do. So for example, if they ask you to calculate the total current in the event of an RLC circuit, so what do you have to do? So your I total is going to be square root of IR squared plus IL minus IC squared. Or if you are dealing with the case where IC is bigger than IL, so you're going to have to do your total current is equal to square root of IR squared plus IC minus IL squared. So that's it. That's how you calculate. So if you notice, you're going to notice that your parallel total current calculation is similar to your series. So in parallel, you apply the Pythagoras formula when you are calculating your total current. In series, the Pythagoras formula is applied when you are calculating your impedance. Now, number 2, if they ask you in parallel to determine now the impedance Z, this is where you apply simple Ohm's law. This is where you apply simply Ohm's law. So after you apply Ohm's law, so it's very simple. Your Z is equal to V total, the total current, the supplied voltage, divided by I total. That's how you determine your impedance of the circuit in parallel. Because in series, it's a different story. In series, so you can see that they oppose each other. A series circuit and a parallel circuit, they are kind of opposing each other in a way where you calculate the current and the impedance. So number 3, they would ask you to calculate. Remember, The parallel circuit is a current circuit. So when they ask you to calculate the phase angle, your phase angle, so you are not dealing, remember here in series when we were calculating the phase angle, we were dealing with the XL and XC and R. Here we were in series, we are dealing with XL, XC, XL. Let me not put it like this. So when we asked to calculate the phase angle, it was all about XL, XC, R. That's what we did in a series circuit. In a parallel circuit, when they ask you to calculate the phase angle, so we are dealing with IL, IC, IR. That's what we are dealing with. So if you have a case where they ask you to calculate the phase angle for an RL circuit, so for an RL circuit, how do you calculate the phase angle? So you have the phase angle equal to 10 to the power negative 1 multiplied by IL, because here we have determined our IR and we have determined our IL. So this is how we plug it in the formula. IL over IR. R is always in the denominator. If you have to calculate it in a RC circuit, your phase angle is going to be equal to 10 to the power negative 1 multiplied by, I'm going to put multiply by IC over IR. Your R is always the denominator. So you have determined your IR, you have determined your IC, and then you plug them in the formula there. So if you have to calculate the phase angle for a RLC circuit, so for an ILC circuit, you also have to make sure, again, for an RLC circuit, let me redo that. For a RLC circuit, so you know if your IL is bigger than your IC, then you are doing IL minus IC. If your IC is bigger than your IL, then you are doing IC minus IL. So that's what we're doing. So in this case, so when you are dealing with the case where your IL is bigger than your IC, your angle is going to be equal to 10 to the power negative 1. Now on your numerator is going to be IL minus IC over IR. That's it. So if you are dealing with the case where your IC is bigger than your IL, your angle is going to be 10 to the power negative 1 multiplied by IC minus IL over IR. So that's it. And they might also ask you number 4 to draw the phasor diagram, but we discussed about phasor diagram, but that is it. Okay, so point 1 was too long, the RLC circuit. This was a long thing, so we had like 27 different points to develop, to discuss on. So we had to come back on other things that we have done in previous videos, just for your clear understanding. So let's go to point 2. Point 2 is about filters. So filters, what do we have to know? Because there's a lot of questions on filters. Explain frequency selectivity. Frequency selectivity is the ability of a circuit. You should be able to explain this. This is the easiest thing you can ever explain. You can lose those 2 marks. They always come 2 marks. What do you understand by frequency selectivity? The ability of a circuit to select a certain range of frequency and reject the other. So that is where we talk about high. So frequency selectivity is the ability of a circuit to select a certain range of frequency and reject the others. Verify that with your notes and choose the easiest and simplest way of explaining that for you. Explain low pass filter. Low pass filter is the ability of a frequency to select low ranges of frequency. So we select here, we select low ranges of frequency, and rejects the high range of frequency. So the high range is rejected, low range is selected, high range is rejected. And the opposite with a high pass filter. So a high pass filter will select the high range of frequency and rejects the lowest range. So it's going to select the highest ranges of frequency and rejects the lowest range. Draw a fully, so if we have to discuss in terms of, if we have to go straight to point 6 before we go to point 4 and 5, if we have to go to point 6, so this will be your high pass. So this will be so these are your frequencies, your output. So your low pass filter response curve, your low pass filter response curve is gonna accept the lowest frequency, because your frequency is increasing from 0 to high. So it's gonna accept the lowest frequency, and when it reaches a certain high level of frequency, and then block all the highest frequency. That's what's happening with a low pass. This is a low pass, so it allows the low frequency to pass and blocks the high frequency. A high pass, so just you explain it as the name, as you call it. High pass, what does a high pass do? A high pass will block all the lowest frequency, and the moment it starts reaching the high frequency, then it starts allowing or letting all the high frequency pass. That's what's happening with low and high frequency. So that's it. So they may ask you in exam to draw the high pass filters. So high pass filters. Let's start with low pass. So on one side we draw the low pass filter, and on the other side we draw high pass filter. So you can have a low pass filter with an RC circuit, RC and RL circuit. It's possible, and there is also a high pass filter for RC circuits and RL circuits. Possible. So with a RC circuit, a low pass filter, RC circuit, a low pass filter is gonna have a resistor and a capacitor. The output is connected across a capacitor. That's how it goes. So there's your outputs. So V in, V out. So RC. So that is your low pass filter, your RC low pass filter. So in case you are asked to draw a circuit diagram showing a low pass RC filter, you're gonna have something that looks like this. So your inputs is through the resistor and your output is connected across the capacitor. That's it. So, and if you're asked to draw a high pass RC filter, so your input is going through, it's just going to be the opposite. You're just going to change. Instead of going in through the resistor, you go in through the capacitor, and your output now is connected across a resistor. That's your high pass filter. So you have V in here, V out there, and then this is R, this is C. Now when it's RL, remember we said a resistor and inductor and capacitor kind of complement each other. From here you can easily make up how RL is going to look. So our RL low pass filter is actually going to be here. Instead of having a resistor, you have an inductor first as a low pass, and then a resistor. Your output is connected across the resistor like that. So V in, V out. So this is RL. It's still low pass, and the response curve is still gonna be the same. So if they ask you to draw the response curve for these two curves, it's still the same. The two curves gives you the same response curve. So it's gonna accept the low frequency and blocks out all the high frequency. That's what's happening. All these ranges here, it's the high frequencies that accept and blocks out. The low frequency accepted. So these are low frequencies accepted here and blocks out all the high frequency. You see, as the frequency is increasing, your response curve is dropping. That's curve apply for the two of them, for R and C, and R and L. If they ask you to draw an RL circuit, high pass filter RL circuits, so you have to, so from the high pass RC, I can easily make it up. So I can come up with, first intro is the resistor. Here the intro was the capacitor. Here we start with, it's gonna be the opposite. We don't do intro with the inductor, we do intro with the resistor. V in comes in through a resistor, R, and then your output is connected across an inductor. And that's how it is. So V in here, V out there. So, and the response curve, if they ask you to draw the response curve for these two circuits, this high pass circuit, so what happens here? It blocks out all the low frequency and allows the high frequency to pass through. That's what's happening there. So that's the response curve for the high pass filter. So yes, you can go through that, study more theories on that, like study all the theories, what's happening there. So yeah, that is it for the filter. For the resonance circuit, so there are a little bit of few things to study there with point 3, resonance circuit. Explain what is a resonance circuit. A resonance circuit is a circuit where inductive reactance is equal to the capacitive reactance. There's a few things also that you can study there, but this is the basics. This is the basic. So when you have a case where XL is equal to XC, that circuit is called resonance circuit. It's a resonance circuit. If you have a case where XL is bigger than XC, that circuit is called capacitive circuits. Inductive circuits. The circuit is inductive. And if you have a case where XC is bigger than XL, that is a capacitive circuit. So that's easy as that. And then you can the response curve for a band pass filter, and then some application. This is point 3. Applications for resonance circuits. So you studied applications of all resonance circuits. And in general, this is everything we need to know about. You can go further and get more information, but mostly this is it. All right. So we're gonna, for question 1, we're gonna solve 2023 question paper, 16 November 2023. This question paper was downloaded from NCV exam paper app. So it's an app on your app store. So you just type NCV exam paper, you can download the app, and so some of you I know have been using this question paper. So some of you, those of you didn't have a chance or were looking for past papers, you can use the app NCV exam papers and download your question papers from there. All question papers are there. All right, so question 1, let's see how was question 1. Question 1, 1.1, they say list 4 applications for resonance circuits. So we've discussed about the resonance circuits. So some of the application would be tuned amplifier, radio frequencies. That's where they are used, because the applications is actually the uses where it is used. So 1.2, with the aid of a circuit diagram distinguish between the low and high pass filter circuits in an RL series circuit? You see, when you get to a question like this, when they ask you for a low and high pass RL, you don't just study RL. You can also study like RC, because you don't know if the same question is going to be repeated or they're going to switch to RC. So low pass filter, here we're going to discuss low pass filter, low pass filter, and on the other side we're going to do high pass filter. High pass filter. So that's it. So when we are dealing with RL, it's RL that they want us to draw RL. So an RL low pass filter starts with an inductor on the input, and then the output is connected across a resistor. So that's how it is. That's it. So you do like this. So they didn't ask you to explain. If they ask you to explain, please read also about explaining, because next time the examiner might not ask you about drawing, they might ask you about explaining. So it's the same question asked in different forms. So that is your V out. So you can build your high pass from your low pass. You see, your low pass, the signal is entering through the inductor. Here on your high pass, your signal is gonna go in through the resistor, and your output is connected across an inductor. That is your high pass. So as we said in our guideline that we are discussing earlier, study also the guideline, the response curve. So this is the case of RL. But what if they ask the same question for RC? They ask you a low pass for RC, so it should be easier, because the RC is just going to be the opposite. Where the inductor was used, you don't use the inductor, it's the opposite, you use the resistor. So for a low pass RC, you start with the resistor, and then the capacitor is connected, the output is connected across the capacitor. That's how it is. That's a low pass RC there. So V in and then V out. So for a high pass RC, we build from the low pass RC. So instead of entering through the resistor, we enter through a capacitor, and your output is connected across a resistor. That's what happens. So you have also to study how to explain. How do you obtain the response curve? So like what happens is, for all the low pass, so for high pass, what happened is, as we talked about the response curve, what happens is on the response curve, so the low pass allows or accepts low frequency and blocks out high frequency, and a high pass would block out the low frequency and accept only high frequencies. So that's how it is. So I went a little bit overboard explaining more, but it's just to broaden your mind. You should not just stick to what is asked on a past paper, because the same question is not going to come back as it is. Okay, 1.3. 1.3, a series circuit consists of a 4 ohms resistor, 40 ohms resistor, capacitive reactance. Here they gave us a XC, a capacitive reactance of 60 ohms, and a phase angle. They gave us a phase angle of minus 26.56. So that's what they did there. So they gave us a phase with the current leading. If the voltage is 220 at the frequency of 50 hertz. So let's go to the new page and then do this. So what is the givens? So we are dealing with the RC circuits. We are dealing with a series RLC circuit. We know it's a series RLC because question 1 says the inductive reactance. So we understand that there is an inductor involved also here. So this is a series RLC circuit. So what is given? It's a series circuit. We know it's a series circuit. Automatically you know what you're dealing with. So what is given? The given are a resistor of 40 ohms, a capacitive reactance of 60 ohms, and what else? Let me check quickly. A capacitive reactance of and a phase angle. So phase angle, the angle given of phase angle of minus 26.56. And what else is given? The voltage is given 220 volt and a frequency of 50 hertz. This is very important. This information is very important. So one, they are asking us to calculate the inductive reactance. Let me check just to verify. Calculate the inductive reactance. That's the first thing we need to calculate. Reactive inductance, which means XC. Now at this instance, you don't know how to obtain. You have two possibilities. There are two. Which formula includes XC in? So once you are given, so one formula that includes XC would be, because we consider this to be a RLC series circuits. So one formula that includes XL and XC together in one formula is Z. But here we don't have Z. Z will be R squared plus, if XL is bigger, minus XC. So so we have XC, yes. We don't have XL, that's the unknown, and also we don't have Z, so we cannot use the Z formula. It won't work. The other formula that we can use that includes both of them would be the angle formula, which is angle is given. So the angle is given, which is 10 to the power negative 1 XL minus XC, XL minus XC over R. Over R. So if we can rewrite this, we can write 10 angle equals to XL minus XC over R. So this is possible because we have this, we have the angle, we have XC, and we have R. So the only unknown that we have there is XL. So which makes it easier, because all we can do is just rewrite 10 of minus 26.56 equals XL unknown minus 60 over 40. So that's it. So if let me use my calculator. So all right, so 10 of minus 26.56 is equal to minus, so here we have minus 0.499 equals XL minus 60 over 40. So if we have to cross multiply, so 40 with that and then 1 with this, so we're going to end up with XL minus 60 equals 40 times minus 0.499. So that's what we get there. So what do we get? So we're gonna get XL minus 60 equals to 40 times minus 0.499 is equal to minus 19,96. So from here it makes it easier because we can send minus 60 to the other side. So we're gonna get XL is equal to minus 19.96 minus plus becomes plus 60. So in the end, XL, so minus 19.96 plus 60. In the end, we get a positive answer. So XL is equal to 40,04 ohms. That is the answer for XL. So that's how we got XL. Now, question 2. What is the next thing they're asking? Inductance. So calculate the inductance in millihenry. So they want you specifically to calculate the inductance. This was the inductive reactance. So from the formula, this is point 2. From the formula, XL is equal to 2 pi F that was given to us multiplied by inductance. We can easily calculate the value of inductance. If we plug each value, so XL is 40.04 is equal to 2 pi frequency is 50 Hertz. So the frequency is 50 Hertz, 50 times, so we write times L. L is an unknown. So let's solve all of this. So let me keep this side still. 40.004 equals 2 pi 50 L. So 2 pi times 50 equals, this gives me 314.59 times inductance. So L is still an unknown. So L is obviously, if we have to calculate L, so it's going to be 40. So the number that is together with L is going to become the denominator. So it's going to be 40.04 divided by 134.159. So this gives me 40.04 divided by 314.159. This gives me 0. So the answer is in Henry, 0.127 Henry. So if you have to convert this in millihenry, we're going to have to multiply by 10 to the power 3. So which going to give me, so 0.127 times 10 to the power 3, which is the same as 1000. So this gives me 127 millihenry. So that is the answer. And then is there a third question? So draw the phasor diagram. So before you draw the phasor diagram here, after you calculate, you should first determine between XL and XC which one, because you first have to know XL. Is XL bigger than XC? That's the first thing you need to know. What was XL? XL is 40 here. We got XL as 40.04 there. That was our XL. And our XC was given to us here. It was 60 ohms. So XC is, this is a in capacitive circuits where XC, so we can determine, so before even we draw the phasor diagram, we know that XC is bigger than XL, so which means capacitive reactance. So we are dealing with a capacitive circuit. What happens in a capacitive circuit? In a capacitive circuit, as we said, in a capacitive circuit, in a C circuit, in a capacitive circuit, what happens in a capacitive circuit? The current leads the voltage by 90 degree. That's what happens. The current leads the voltage by 90 degree. In terms of phasor diagram, we have, that's the current, and the voltage will be like that. So we're gonna base all our phasor diagram ideas on this. So that's what we're doing. So if we come here, this is a series circuit. So what is the point of reference in a series circuit? It's the current. So we're gonna draw a horizontal vector pointing to the right. That is our current vector. For a resistor, so what happens with the resistor voltage? The resistor voltage is always in phase with the current. So that is our VR. And now what happens? So because of XL being bigger than XC, this angle is going to be XC minus XL angle. So this angle here, the capacitive angle, this one here, this capacitive vector, is the vector XC over, sorry, we are dealing with voltage. So VC minus VL angle. So, and then we project to somewhere there where we got VL minus VC, and then VC minus VL, sorry, and then we get the V total there. So that's our phasor angle. So it's much easier if you know your foundation here. If you are here, if you know this already, you can do your phasor diagram without any fuss. Alright, so that's all for 2023. Is there another question? That was all. 2023, that was the whole question. So let's go to another paper. We have 2022 paper, also was downloaded from NCV. Also downloaded from NCV exam papers app. So let's go to 2020 question 1. Okay, now this is almost the same thing. So I would let you do this one by yourself. This is straightforward. You are given a resistor in series with a so this is a RC circuit in series with a capacitor, everything connected across a power source. So a resistor of 12 ohms and a capacitor of 100 microfarads. You have to convert the 100 microfarad. This is 100 times 10 to the power negative 6 farad. Don't forget that. You're going to get wrong answers if you don't convert here. You must convert. So even if it's a RL, sometimes they will give you, if it's a RL circuit, they will give you sometimes L in millihenry, like let's say 12 millihenry. You must convert to 12. This is 12 times 10 to the power negative 3 Henry. You have to convert it, otherwise all the answers you're going to get are going to be wrong. So we've converted our C, 100 times 10 to the power negative 6 farad. That's it. So now they ask you to calculate. It's easy. They ask you to, this is the easiest one ever. They ask you to calculate the capacitive reactance XC. It's very easy. 1 over 2 pi FC. That's very easy. You just plug your numbers there, you get it. And now they ask you to calculate the impedance. So once you've calculated your XC, it makes it easier for you to calculate your impedance, which is equal to square root. In a series circuit, you apply the Pythagoras triangle. Square root of R squared plus XL. L squared. This was very easy. The current flowing through the circuit. Since this is a series circuit, there is only one current, and in a series circuit you apply Ohm's law when you are calculating the current. Current is going to be equal to V, the applied voltage. The applied voltage given here was 220 volt divided by Z. So the Z that you find, you're going to have to plug it here to get your total current. Your phase angle. So phase angle also is very easy to calculate. This is a series circuit. We are dealing with a series circuit. So first of all, after you did all your calculations, so you know that you are only dealing with XC. XC is the only one. So so you're gonna have to, your angle here is gonna be 10 to the power negative 1 multiplied by XC over R. So the XC value that you get here, that was this one. So you're gonna have to do it over 12. 12 was given to you there. That's it. Voltage across each resistor, you apply Ohm's law here. For VR, you do I, because there is only one current that you had calculated here, multiplied by resistance, multiplied by 12. For voltage across the capacitor, you do VC is equal to I, not multiply by C. You're not going to multiply it by 100, but you're going to multiply it by the value that you get here from XC. The value that was asked here, XC. That's what you plug there. And that's it. It's 18 marks. This was the easiest question ever. 18 marks for free. I would say for free. If you follow all the steps, don't forget to convert. Converting is the most important thing. That was the easiest question ever. Alright, so there are some true or false. So in an RLC resonance circuit, resonance occurs when XL, this is true. This is true. And here, when the frequency in the bandpass filter increases, the impedance of the circuit decreases. This is false. This is false. So that's it for question 1 for 2022. So yeah, that was easy. So I think we're gonna just go straight to other questions.